All right, so let's take a look at 4 through 8, true, false, and I've jotted down the answers here. First one says, if the limit as x approaches 5 of f of x equals 2, the limit as x approaches 5 of g of x equals 0, then the limit of f over g as x approaches 5 does not exist. That has to be true because the 2 over 0 creates, oops, excuse me for moving the screen, creates some sort of vertical asymptote situation. So the 2 over 0 is why you know that the limit cannot exist. Number 5 says, same situation, different situation, if the limit as x approaches 5 of f of x equals 0 and that limit of g of x as x approaches 5 equals 0, then the limit does not exist. Well, this is the possibility of a hole. If you have a 0 over 0, that could be like x minus, let's do x minus 5 to match. Oop, there we go. That could be this situation of x minus 5 over x minus 5, where this is f of x and this is g of x. And so the limits of each of them are 0, but when you divide, you get 1, and the limit as x approaches 5 of 1 is the number 1. So this is the situation when you've effectively created a hole. So again, to prove something false, you just need one counterexample. Number 6 says, the limit as x approaches 6 of f times g exists, then the limit must be f of x times g of x. That will only hold if it is a continuous function. If you have a hole in this case, f of x, f of 6 could be any number, and g of x could be any number, even if, let's see if I could draw a couple pictures for you. So I have f here with maybe a hole here, and g here with a hole also. And then the f is filled in there, and the g is filled in there. Just because this limit here and this limit here exist does not mean that when I multiply the y values of the function equal to each other, I get the limits multiplied together, because this y value times this y value will give us this situation, but this point times this point will give us this situation. Next, if p is a polynomial, this effectively says the function is continuous. If the limit as x approaches b of the function is equal to the y value of the function, then the function must be continuous. This is the definition of continuity. All polynomials are continuous, therefore this is true. Okay, so number 8 says, if the limit of both f and g as x goes to 0 is infinite, then the limit as x goes to 0 of f minus g is 0. Well, we could think of, first of all, if the limit is infinity as x goes to 0, we have some graph that might look like this. This is one example. But the trick is they're basically saying if you take one infinity minus another infinity, then you are going to get 0. But that is not necessarily true. And I'll just give you an example. Think about the set of all real numbers. And that is an infinite set. It's an infinite number of numbers. And if you subtract off the set of all integers, which is also an infinite set, do you get 0 if you take all the real numbers and take away all the integers? No, you still have an infinite set of all real numbers less all the integers. So you may not state that infinity minus infinity equals 0, and therefore this one is false.